On its first page, the Kimi team gives us a title that already sounds like a verdict. Kimi K3, Open Frontier Intelligence. Those last 3 words are the paper's claim, and our job is to see how much evidence they earn. The model behind that claim stores 2.78 trillion parameters, the adjustable numbers it learned during training. It reads text in small pieces called tokens. For each new token, it activates 104.2 billion parameters, a selected part of the much larger model. Those tokens can form a very long input. K3's training context reaches 1 million tokens, which tells us the model saw inputs at this scale during training. Reliable use across the full span remains a separate question. From here, we follow one chain through the paper. We move from what K3 is made of, through how it is trained and how long tasks pause and continue, to the evidence for scaling efficiency, frontier performance, and openness. We begin with a simple map of the model itself. Our map begins with one token entering K3's 93-layer backbone, the main stack that processes it. The model must decide what this token can use from other token positions, what it can use from earlier layers, and which experts should process it. Start with token positions. For this sequence job, Kimi Delta Attention, or KDA, works alongside a global attention layer called Gated MLA. The stack contains 69 KDA layers and 24 gated MLA layers, mostly arranged as 3 KDA layers followed by 1 gated MLA layer with 1 final MLA layer at the top. Now look upward through the same stack. Block Attention Residuals, or Block Attenres, groups the 93 layers into 8 blocks. A later layer can then choose among the combined outputs of those blocks. The third job is Expert Choice. After every attention layer, Stable LatentMoE selects 16 of 896 routed experts to process the token. Images enter before these 3 jobs begin. A 401 million parameter encoder called Moonshot v2 converts an image into features, and a projector turns those features into the same kind of input the text backbone receives. From there, image and text use the same 93-layer backbone. The 1 million token training context from our opening now has a place on this map. It belongs to the sequence axis, where useful information may need to travel between positions very far apart. KDA and Gated MLA share that job. Take the highlighted token at the end of our 1 million token row. In Gated MLA, every token leaves 1 compressed key value entry in the cache. Each new token adds another, so each global attention layer can hold up to 1 million entries. KDA replaces that growing row with 1 fixed shape matrix. A new key acts like an address. KDA reduces the old value at that address, then writes the new value there. Before that write, KDA scales each matrix row with its own retention number. A smaller number makes one row fade faster, while a larger number preserves another longer. The paper calls this channel-wise decay. The fixed shape has a cost. It cannot keep a separate slot for every old token. Writes can interfere, details can fade or be replaced, and a query can read only the summary that survived. Gated MLA keeps 1 compressed entry per token, so the current token can reach any earlier token directly. K3 repeats 3 fixed state KDA layers followed by 1 gated MLA layer, then adds a final MLA layer. Most attention layers avoid a growing cache, while regular global layers restore direct access. Here we hit a numerical instability. To process 16 tokens together, KDA divides by their accumulated retention. If those retention values multiply too close to 0, the reciprocal can exceed what the number format can store. K3 keeps each step's log decay above -5. Across 16 tokens, the cumulative log decay stays above -80, so the reciprocal remains below e to the 80 and fits in BF16. Every causal tile can then use dense matrix multiplication on the GPU's tensor cores instead of a special position pair calculation. Across tokens, K3 uses fixed recurrent state in most attention layers and regular global access through Gated MLA. The same backbone still has to move useful information upward through 93 layers. follow one token upward through the 93-layer stack we left on screen. In a standard residual path, each layer adds its output to one running state. By a later layer, the original embedding and every earlier result have been merged into that single state. Full attention residuals keeps the earlier results as separate choices. Each layer owns one learned query, fixed for that layer, which scores the embedding and each earlier layer output. Those outputs change with the token, so the weights also change with the token's content. We gain choice, but all of those choices must stay available. Near the top of a 93-layer model, that means storing the embedding and almost every earlier output. When training is split across devices, some of that history must move too. Keeping and moving it is the larger cost. Block attention residuals shrinks that history by adding the outputs inside each block into one summary. Different block summaries stay separate, so a later layer can still reach far down the stack. It chooses a block summary rather than one exact layer output. Now count K3's blocks. 7 contain 12 layers, and the final block contains 9, covering all 93 layers. The retained completed history grows by one summary per block rather than one output per layer. Inside the current block, outputs build one partial sum. The first layer can choose the embedding and the finished block summaries. Later layers can also choose the partial sum forming in their own block. At the final output, the embedding plus 8 completed block summaries make 9 depth sources. Across depth, K3 replaces one uniform running sum with content-dependent selection over this bounded set of block sums. That leaves width as the next limit, giving one token more expert capacity without activating all 2.78 trillion parameters. Keep following the token from the depth stack. K3 stores 2.78 trillion parameters, but processing that token activates 104.2 billion. Most of the model stays idle for that token. Inside each expert layer, a router sends the token to 16 of 896 routed experts. 2 shared experts also process every token. The other 880 routed experts are not run for this token. Before those 16 routed experts receive it, K3 reduces the token's 7,168 number state to a 3,584 number latent vector, a smaller internal representation. The shared experts keep the full width input. The selected routed outputs are mixed and expanded back to 7,168. This narrow route adds a stability problem. It chains almost 4 matrix multiplications, and the usual Swiglu step multiplies 2 values with no upper bound. If both grow large, their product can overflow the low precision number format. K3 replaces that step with situ glue. It smoothly caps one factor at 4 and the other at 25, so every output coordinate has absolute value at most 100. Around small values, it stays close to the uncapped function. The 16 selected outputs are weighted and added, so their combined scale can vary with the experts and router weights. Before expanding that mixture back to full width, K3 applies RMS norm, which rescales it and reduces this sensitivity. Stable numbers can still leave the traffic uneven. In the paper's small example, 8 tokens each choose one of 4 experts. Plain top 1 routing gives them loads of 4, 3, 1, and 0. Quantile balancing looks at how close each expert came to being selected for each token, then computes an expert-specific bias for the next batch. Applied to these worked scores, 3 routes change, turning 4, 3, 1, 0 into 2, 2, 2, 2. Training freezes the final biases for inference. K3 can store 2.78 trillion parameters without running every one for every token, while explicit controls limit activation size and spread the training load. With that capacity in place, training determines whether the model can sustain long, tool-using behavior. Our token now has plenty of model capacity behind it. During pre-training, its job is to predict what comes next. To handle a long agent task, K3 needs a learned loop that chooses a step, calls a tool, reads the result, then continues. Training begins with sequences of 8,000 tokens, then grows to 64,000. Late in training, the limit rises to 256,000, then 1 million. The longest sequences cost the most to process, so the team concentrates them in a small part of training. That last stage establishes exposure to 1 million token sequences. Reliable use across the whole window needs a separate test, such as measuring recall or reasoning at many positions. The report provides no controlled curve like that. With the window widened, verified examples teach a starting policy, the model's learned way of choosing what to do next. Each example contains the agent loop we saw. Reason, call a tool, observe, and continue. The team next guides training with rewards, a method called reinforcement learning. They divide the work into 3 domains: general tasks, general agents, and coding agents, and train 1 specialist for each. Inside each domain, the team starts with max effort and a relatively large token budget. They tighten that budget to produce high and low effort versions. A run that exceeds its budget receives a reward of -1, so effort becomes learned behavior. Put the 3 domains down the rows and low, high, and max effort across the columns. They train 1 specialist in every cell, giving 9 policies. K3 still needs 1 policy that covers all 9. Now, one shared student, the policy meant for deployment, generates its own trajectory. The specialist matching that domain and effort becomes the teacher and scores each student token. This is on policy distillation because the current student produced the work being scored. Repeat this across all 9 cells and 1 policy learns from every specialist. Each training trajectory includes its chosen effort setting. The deployed model's low, high, and max choices are part of the learned policy. One student trajectory can keep growing through thousands of tool calls and millions of accumulated context tokens. Shorter runs may finish while it is still active, and training cannot wait for every straggler. The system now has to pause that unfinished work without losing where it was. A policy update is ready, but our long trajectory is still running. K3 does not hold the whole training round for it. Finished groups move into the update, while unfinished work pauses in a priority queue and resumes in a later round. When our trajectory returns, the policy may be newer than the one that began it. Its prefix, everything the model has processed so far, must restore the model state at the pause point, so generation can continue instead of starting over. While the trajectory is active, its decoding blocks stay in GPU memory. If it becomes idle and the GPU needs room, K3 writes the prefix to CPU memory, then fetches it back before resuming. The fixed KDA state and the growing MLA cache move together. CPU memory also fills up. At the end of a training iteration, K3 moves the model weights and optimizer state to NVMe storage, opening CPU memory for rollout prefixes. After rollout, the prefix pool is released before training resumes. The model prefix preserves the conversation, while a coding task also has files, tools, and a live workspace. Agent env keeps that workspace in a micro VM, a small isolated virtual computer, and checkpoints only memory pages changed since the previous snapshot. While the sandbox waits for the model's next response, its micro VM can pause without using CPU or memory. Resume both the prefix and the micro VM, and the next action sees the same conversation and workspace. Now split one long sequence across 3 devices. The second segment cannot produce its exact result until it knows the state left by the first. Processing every token in order would leave the devices waiting on one another. KDA lets each segment prepare a compact pair. One part describes how the segment changes any incoming state. The other records what the segment writes from 0. Together they form an affine transition from the incoming state to the exact outgoing state. Each device computes its pair before the earlier state arrives. Then the pairs combine in order, letting every device reconstruct its own incoming state. The messages stay fixed in size even as each segment contains more tokens. In K3's system, a 1 million token agent stays alive only if its model state, environment state, and cross-device state survive every pause and handoff. With the design path complete, we can examine the evidence behind the paper's reported 2.5 times efficiency number. Our K3 system map is complete, and its scaling box still reads 2.5 times with a question mark. In the report, that number comes from the horizontal distance between fitted K2 and K3 compute curves. Each star on this chart marks one experiment. Left to right is flops, the amount of calculation work. Up and down is validation loss, an error score on held out data, where lower is better. The dashed lines are fitted trends through those experiments. Pick one validation loss and move sideways until both fitted lines meet it. If K2 needed 5 equal compute blocks there, a 2.5 times gap puts K3 at 2 because 5 divided by 2 is 2.5. The paper's claim is the same ratio. K3 reaches that fitted loss with about 40% of K2's flops. Try to recompute that ratio from the report alone. The chart has no numerical validation loss ticks or coordinates for its plotted experiments, and the report gives no fit equation, measure of fit error, or uncertainty range. The report does not let us independently repeat the calculation. The cause is less specific than the number. K2 and K3 differ together in layers: parameter count, attention, training context, data, optimizer settings, and schedule. The curves compare two full training families, so they cannot assign a share of the gain to KDA, AttenRes, or any other single change. The smaller Kimi linear study holds much more of the recipe fixed. Across 5 model sizes, from 653 million to 1.7 billion active parameters, it compares full MLA with the 3:1 KDA hybrid and reports about 1.16 times fitted compute efficiency for the hybrid. This cleaner, smaller scale result supports the narrower claim that hybrid attention can help. Attention Residuals gets a separate test. 5 model sizes, from 194 to 528 million active parameters, compare the usual residual path with block AttenRes under the baseline recipe. At one fixed compute budget, fitted loss is 1.714 for the baseline and 1.692 for block AttenRes, and the paper reports a 1.25 times compute advantage. These companion numbers stay separate. They come from different models and training setups, not from independent factors measured inside K3. Multiplying them would make a new claim that none of the papers tested. So the scaling box gets a precise label. The authors report a 2.5 times family fit, with narrower support for KDA and AttenRes at smaller scales. The frontier box now asks what K3 can do and where it fails. That efficiency result still leaves K3's capabilities and failures unresolved. The paper's agent table gives us one strong result and one clear gap. K3 reaches 91.2 on the search task BrowseComp, above GPT-5.6 Sol at 90.4, and Fable 5 at 88.0, then scores 58.3 on the computer use task OSWorld 2.0, below 62.6 and 66.1. The split appears in coding too. K3 scores 77.8 on Program Bench, ahead of GPT-5.6 Sol at 77.6 and Fable 5 at 76.8. On DeepSuite, K3 67.5 trails 73.0 and 70.0. The report therefore says K3 still trails Fable 5 and GPT-5.6 Sol overall. Read the small gaps with care. The coding comparisons use different harnesses for different model families. Across the table, models run at their maximum or listed effort. Fable 5 may use fallbacks, and GPT 5.6 Sol may apply cyberguards. Each gap, therefore, includes differences in how the systems were run. Artificial analysis provides an independent check. It tested K3 through Moonshot's API and gave the model 57 on its v4.1 intelligence index. In its July 17 snapshot, K3 ranked behind Fable 5 and GPT 5.6 Sol and roughly level with Opus 4.8 and GPT 5.5. That result places K3 near the leading group. The weighting behind 57 matters. Agents contribute 34% and coding 24%, so those two areas make 58% of the index. Scientific reasoning contributes 24% and general tasks 18%. Vision and multilingual tests sit outside this score. One knowledge result keeps capability and reliability apart. K3 answered 46% correctly, up from K2.6's 33%. Its reported hallucination rate also rose from 39 to 51%, so it committed to more false answers while getting more answers right. That gives the Frontier box its final label, near the leading group, strongest in agentic encoding work, with uneven results across tasks and reliability. The remaining word in the title is open, and we can test it against the files people can download. That stack holds the part of K3 we can check most directly. The public repository has 96 weight files totaling about 1.56 terabytes with no access gate. Weights are the stored numbers a model learned, and these files hold the quantized K3 target model. Beside the weights, a machine-readable configuration tells software how to assemble them. It specifies 93 layers, 69 KDA and 24 gated MLA layers, 896 routed experts with 16 chosen per token, a 1,048,576 token limit, and a 27-layer vision tower. Those settings match the report's core architecture. The custom license allows use, modification, distribution, sale, deployment, and fine-tuning, with 2 conditions at large commercial scale. A licensee or affiliate that runs a model service and has more than $20 million in aggregate revenue over any consecutive 12 months needs a separate Moonshot agreement before commercial use. A commercial product above 100 million monthly users or $20 million in monthly revenue must display Kimi K3 prominently. Internal use and use through Moonshot's official products or certified inference partners are exempt from both conditions. Open weight under a custom license is the precise label. Here, open weight means the trained weights are available to download and inspect. Reproducing their creation requires a different set of artifacts. The inspected file list contains no pre-training or post-training data, intermediate checkpoints, optimizer state, or scaling law measurements. Another team therefore cannot reproduce K3's training or rebuild the 2.5 times scaling fit from this repository. Most of the code and setups used to run the evaluations are also absent, so the paper's reported scores cannot be rerun from this repository alone. The speculative draft model described in the report is missing from the main artifact too. Its configuration sets next token prediction layers to 0, and the file list contains no separate draft checkpoint. The word open now has a precise meaning for K3. The release provides a substantial target model artifact under a custom license with commercial conditions. Training and most evaluation remain unreproducible from the inspected repository. That is the last evidence label we need before judging the full title. Now the full title is back in front of us, Open Frontier Intelligence. We can judge the model itself, its frontier status, and what open means as 3 separate claims. K3 is a real released model. Its roughly 1.56 terabyte quantized target weights are public, and the machine-readable configuration matches the 93-layer architecture we followed across sequence, depth, and experts. Frontier is defensible as a tier, especially for coding and long-horizon agent work. Independent testing places K3 near the leading group, with uneven results and reliability across tasks. Open means open weight here. The target model is downloadable and inspectable under a custom license, while training and most evaluation remain unreproducible from the inspected repository. The exact 2.5 times scaling gain remains author-reported. The release records do not let another team reconstruct the family-level fit, and many reported systems improvements lack measurements that another team can rerun. We still lack a controlled measure of useful performance across the full 1 million token window and K3 scale tests that isolate what each major component contributes. K3 is a significant open-weight systems achievement, with a coherent design and a credible frontier agentic profile. We can explain how its main pieces work more confidently than we can say how much each piece caused the final gains.